As the temperature is raised, some polymers melt from a regular three-dimensional crystal to a smectic phase, then to a nematic phase, and then finally to an isotropic melt. How would the appropriate differential scanning calorimetry curve look for such a polymer? So since the crystal is moving to a smectic phase and then to a nematic phase and then finally to the isotropic melt, each of these transitions is a first order transition, and so we'll get a multiple endotherms, or rather three endotherms for each of these phase transitions. This is the temperature axis, delta T here. So there would be three peaks. First is the transition to the smectic phase, and then transition to the nematic phase, and then transition to the isotropic phase. So let's call it A, B, and C. Based on figure 7.10, discuss whether lyotropic polymer systems exhibit two or more phases simultaneously, and if so, under what conditions. So this is figure 7.10, and it is a plot of the volume fraction of the polymer Vp on the x-axis and chi, which is the Flory-Huggins parameter, on the y-axis. So there are three regions. On the left is the isotropic phase, where at very low concentrations of the polymer or in very dilute solutions, it is mainly isotropic. And then we have this heterogeneous area where you have isotropic and anisotropic coexisting, and then on the right you have just the anisotropic region. As the concentrations of the polymer increases, there is more anisotropy. At this point, we have all the three phases coexisting with each other, and that's the triple point, the anisotropic, and then there is some heterogeneous and isotropic. Heterogeneous is a biphase area where you find both isotropic and anisotropic polymers. So this is a triple point, and this corresponds to about 0.07 for the chi value. So Flory observed a transition from complete disorder, which is isotropy, to partial order with a change in concentration, and it was observed that it followed this equation: V2 star equals 8 over x times 1 minus 2 over x, where V2 star is the critical volume concentration, when you find the abrupt change from complete disorder to partial order. And here x is the aspect ratio. It's also called the axial ratio, and which it's equal to 100, where 100 is the ratio of the length of the polymer rod, the length of the liquid crystal rod, to its radius. So if we plug in the values here, V2 star we get is 8 over 100 times 1 minus 2 over 100, so 0.0064, and that matches with the value of chi corresponding to the critical point, which is 0.07. All the three phases coexist at the critical point. There are three major types of polymers: semicrystalline, liquid crystalline, and amorphous. Give an example of each naming the polymer. Given an unknown polymer, what one experiment would you perform to identify which type you had? What major behavioral differences would you expect among the three types? For part A, an example of semicrystalline polymer would be polyethylene. So polyethylene is semicrystalline at room temperature. An example of liquid crystalline would be polyparaphenylene terephthalamide. An example of amorphous would be polymethyl methacrylate. Polymethyl methacrylate is below its glass transition temperature at room temperature. Um, Polyethylene is above its glass transition temperature at room temperature. Given an unknown polymer, what one experiment would you perform to identify which type you had? We can heat the polymer and study the effect on temperature. For a semicrystalline polymer like polyethylene, the graph of temperature versus heat would be like this. It will undergo a first order transition at its melting point, whereas an amorphous polymer will undergo a second order transition at its glass transition temperature. A liquid crystalline polymer behaves like this with increase in temperature. The polymer will first melt into the smectic mesophase, and then with further increase in temperature, it will do a first order transition to the nematic phase. and with further increase in temperature, it undergoes another first order transition to the isotropic phase. The polymer is a liquid here, and here it is an anisotropic, and these are all first order transitions. What major behavioral differences would you expect among the three types? Regarding mechanical properties, amorphous polymers have less tensile strength compared to crystalline polymers. Crystalline polymers tend to have higher tensile strength. Liquid crystalline polymers have very high tensile strength, especially rod-like shaped polymers, which is why they are used in making high tensile strength fibers. The density of crystalline polymers is higher than that of amorphous polymers, and liquid crystalline polymers also have high density. Chemical resistance is extremely high in liquid crystalline polymers. Chemical resistance of crystalline polymers is higher than that of amorphous. Compare and contrast the intrinsic viscosity Mark-Houwink Sakurada value A for rigid rods and random coils. Why is the viscosity higher for rigid rods in the case of dilute solutions but lower in the case of concentrated solutions? So let's start by writing the Mark-Houwink Sakurada equation, which is eta equals kmv to the power A, where eta is the intrinsic viscosity mv is the viscosity average molecular weight, of the polymer, and K and A are the Mark-Houwink Sakurada constants. Now, A is 0.5 to 0.8 for random coils and the value of A is 2.0 for rods. In dilute solutions, rigid polymers are in the nematic mesophase, and so there is lack of molecular entanglements in this phase, which is why the viscosity is less as compared to the random coils, which are entangled with one another. At high concentrations, the liquid crystalline polymers are in smectic phase, and there is strong intermolecular attraction between the polymers molecules, and so the viscosity is higher as compared to that of the random coils, where the molecular attraction is less because the polymer chains are randomly arranged as compared to the liquid crystalline polymer, which is in smectic phase, and the molecular layers have strong forces of attraction. So this increases the viscosity of the shear flow.